soon find out more about it. Let me just say that I'll be your moderator for today. And in this agenda, we have 7 amazing speakers telling you all about the different aspects of this project. And we'll start by hearing from the coordinator of the project, Julio Illade Quintero, the researcher from IMEN. And later we hear the presentations as well of other partners such as IMEC, Photon Focus, University of Vigo, Cinematic, Quest Medical Imaging, and Adwit. And without further delay, I'm glad to introduce to you our first speaker, so Julio Illade. Welcome, Julio.
Hello, thank you. Thank you, Ivan.
It's good to have you and all of us here together. So please, whenever you're ready, the floor is yours.
Sure. Let me share my screen. Okay, you can see my screen, right?
Yes.
Okay. So hello, everybody. I'm glad to be here presenting the RETINA project. I think I have the easy job because I just have to show you an overview of the project and the coordination. Later on, my colleagues will show you the technical details and the more complex stuff. So this is a little bit what I'm going to do, and I will go from less important to more important, starting presenting myself, then my research center, and after that the project. So I'm not going to waste a lot of time because we don't have a lot of time for this presentation. So for my part, just I'm going to say my name is Julio Illade. I'm the project coordinator for this project. I worked at IMEN for the last 5 years at the signal processing group, and you have there my contact if you want more information related to IMEN or to this project. Okay, I put here my photo because I didn't know if we will see each other through Zoom, but there you go. Okay, so I'm not going to lose a lot of time introducing also IMEN, but please let me, for those of you who don't know IMEN, let me show you a little bit who we are. We are a private non-profit research center. We were established in 1977. And we were created from an association of industries in the north of Spain. And you can see here the division of industry that more or less stayed the same through all the 50 years. Mostly it was related to the metal industry. So most of our research is done here, but we have developed a lot of other sectorial interests. Actually, we are 300 members from IMEN, 300 employees, and we have facilities to develop all our programs and to demonstrate a lot of different use cases and a lot of different technologies. We work mostly through publicly and private funded projects. Half of it is more or less, or a little bit more, is about public funding projects, and the other almost half is about industrial partnership with other companies or services that we provide to other companies. In the R&D division, we specialize in circular economy projects, Industry 4.0 and all of this. And we are mostly active in these sectors that you can see below here. Sorry, one moment. Okay, thank you. Okay, so this is more or less what I'm going to talk about IMEN. You have more information in the webpage, and you, of course, can ask me whatever you want. Related to the RETINA project, I wanted to first introduce the funding opportunity that we take advantage of for this project. is this Horizon Europe program. And what it asked for, it was project related to novel or next generation sensory photonic technologies, and it wanted to address some of these sectors. It's a very complicated, in my opinion, proposal, or very complicated project, especially because it asked to start in TRL 3 and to move to TRL 6.7. It's a lot of advance. Even if it's a 4-year project, it's still a little bit difficult. But we have several contacts and different technologies we were interested in developing, and we saw this as a good opportunity. More or less, the idea, if I'm able to summarize the idea of the project in a slide, will be something like this. We are proposing 2 different photonic technologies, although 2 is maybe too reductive, but and we are proposing coupling it with machine learning algorithms. So the 2 technologies that we are proposing is a novel LiDAR based on photonic integrated circuits, and the other one are spectral, hyperspectral imagers, snapshot imagers that in reality they are developed in 3 different technologies. I think Carolina from IMEC will give you more details, but the idea is to develop hyperspectral images that can work not as a push broom or not as a scanning device, but they are able to take the entire spectral image in one round. As I said, besides this, we wanted to couple this with machine learning algorithms to show the potential of these new sensors to extract high-level information of the environment. And we will demonstrate or validate this in 3 different sectors, in 3 different use cases that you can see here below. The healthcare use case, the automotive use case, and the agriculture use case. I think, if I'm not wrong, we have 1 person from each of these use cases to give you more details. Regarding the consortium, it's a big consortium. We are 13 members, as you can see here. We are from 7 different countries, and we span from research centers to large companies and to even a hospital. And we think that with this consortium, we are able to work through all the steps from TRL 3 to TRL 7, from the development of the sensor to having a validation platform that will helpfully show in these sectors the usefulness of the new sensors. So I'm going to summarize a little bit these technologies that we are developing here. As I said, I'm not going to give much detail because first, it's not my field, and second, we have here people more prepared that will give you more in-depth view of the sensors. But just for you to have an idea, the LiDAR that we are developing, the main advantage that we have is that we will base it in a tilted grating couple array. So the beam steering can be done electronically. So we don't have any mechanical components. We can make it smaller, cheaper, and more robust because of this. And we also have the frequency modulated continuous wavelength modulation. So we can, in addition to have the position of the objects in the environment, we can also have their speeds, for example, which I think is a good advantage in a lot of fields. In addition to this, we have snapshot spectral imagers. As I said, we have 3 different technologies. IMEC is developing quantum dot imagers, but also it's developing for the visible and near infrared and for the SWIR range, different technologies based in CMOS or in gas sensors that can be applied directly to the sensor. Sorry, Caroline, I know that I'm not doing a very good job explaining this, but I know that you will do it better in your presentation. And in addition to this, we wanted to take seriously the machine learning algorithms that we will validate in the use cases scenarios. So we are associated with Abraya platform. It's a small company that is developing a platform for machine learning exclusively or specifically for this type of data, for hyperspectral data and for point cloud data. And the idea is to develop all the pipeline of the machine learning from the labeling of the data to the deployment of the algorithms in a single platform. Okay, and for the use cases, as I said, we have these 3 use cases. Again, I'm not going to enter in much detail because we only have 10 minutes to present the project, and because other people after me are going to give better insight of this. But the idea for the healthcare use case is to have an AR platform that will allow surgeons to have more information regarding tumor cell and regarding oxygenation of blood streams and things like that. It will use the short-range version of the LiDAR because we will have 2 LiDAR developments, one for the short range and other for long range. And it will use SWIR and visible and near spectral images also to obtain the spectral information that will allow this extra high-level detail for the surgeons. In the case of others, we are focusing our work in the long-range LiDAR. We want to show the advantage of the LiDAR that we are developing in this sector because we know that it's a key sector for the future LiDAR devices. But we are also coupling it with a commercial camera to work on the data fusion and see how well we can mix this information and extract as much information as possible from this data. And for the third use case, for the viticulture use case, we will have not 1, but 2 validation platforms. And the idea is to show how these sensors are better suited for the state-of-the-art applications or services that are right now working in agriculture. This is mostly drone-based sensors, but also we wanted also to show the possibilities that this new sensor will have in proximal data. It's working closer to the plant, not in a drone 60 or 40 meters over the field, but just operated at a half meter or a meter from the plant and see how much information we can obtain this close to the plant, because we think that it's the future of the sensor to work closer to the plant. I think that this is a little bit of everything. Here we have a schematic of how each sensor will be deployed in each use case, because we will have, as I said, 2 versions of the LiDAR, and we will have several versions of the spectral imagers deployed in several types of cameras, and each one will apply to a different use case. If you have more questions regarding this, you can ask me after this. Oh, yes, sorry. The last part will be, I wanted to show what we are going to do. I meant the research center in this project. We are not only coordinating the project. I'm not saying that this is not a difficult task or it will take a lot of effort, but we are also involved in the technical part, especially in the low-level signal processing. We are not involved in the development of the sensors, but we are working closely to the developers because we will do the low-level signal processing of the data that goes out from the sensors. and we are also developed in the validation of the viticulture use case, because we are the ones that we will work in the machine learning algorithms and in the validation platform. Okay, I think that's all. Yes, this is all. Ivan, I don't know if it was too quick or too slow.
No, it was perfect. Thank you, Julio. Very nice summary. I think everybody understood the scope of the project, and I'm sure there might be people interested in more details. So we have 6 more speakers to cover every little aspect. So just to remind everyone that, yeah, so today after each session, after each presentation, we have a little question and answer session. So please feel free to participate in it. You just need to click on the raise hand button at the bottom of your Zoom screen, and I pass you the word when possible. So if you think of a question, don't hesitate. And in the meantime, I'll ask Julio myself. Look, I'm wondering what kind of exploitation results you aim to achieve at Retina. What kind of exploitation of the project is assumed for the future?
You mean as I meant specifically?
No, as well as all of the consortium. Yeah.
Oh yeah, as well of the World Consortium. Yes. Okay. First, we have the developed sensors that will be commercialized by itself. Besides this, the commercial sensors are being developed. The spectral images by IMEC, and the LiDAR is being developed by the University of Vigo and fabricated by Fraunhofer. So these sensors will probably be as an individual K development that can be exploited independently of the rest, but also this LiDAR will be integrated in a device that can be used, not just the sensor, but the signal processing in an individual platform, so it can be used for other applications. And the image sensors will be integrated by photon focus in cameras that will also add embedded machine learning capability, so the camera will be able to capture the image and do some low-level processing. So this will be all exploitation results that will be commercialized individually. Quest, of course, will commercialize. I think Richard can give more information if I'm wrong. The medical device that is going to be developed. And the Abraya platform will also be developed here, but will be open to any client that want to work with hyperspectral data and point clouds and needs a platform to do the machine learning and the labeling and the training of this machine learning. Besides this, depending of how well the validation platforms work, we will work with thematics to see how exploitable these are as individual results. And IMEN by itself is more interested in the capabilities that we develop and in the knowledge that we develop, because remember, we are a non-profit organization. So of course, if there's anything that we can commercialize or license, we will be interested in doing, but we are also we are mostly interested in getting more knowledge and learning more how these new technologies work and how we can apply them to other industries.
All right. Well, that's a lot of exploitation results indeed.
Yes.
And another question I had in mind is um, more yeah, regarding the details of each of this exploitation result, but also yeah, sorry, there was a technical problem. Yeah, so the question was, so we have over 50 industry experts with us today in the room, and many more will hopefully see this our workshop later in the record. And of course, this kind of project cannot exist independently of the whole value chain of industry. So how could the external partners maybe participate in the project or exchange information? Or is there something that the RETINA project needs from the other members of the value chain of smart sensors?
Yeah. First of all, we are starting just the project, so we are just in the first year of the project. We are still a lot of work to do. I will say right now what will be more interesting will be to understand the needs of the industry regarding this type of sensors. Sorry, because we know or we did a good job of extracting the necessities in the three sectors that we are going to validate the sensors in the agriculture, in the ADAS, and in the healthcare. But for sure, we are not completely understood the needs or the potentiality of these sensors. So regarding the possibilities that the experts see to these sensors will be interesting. Regarding the development of the sensors itself, I think that especially in the LiDAR, there's a lot of work that is going to be done. And I think that Francisco will explain the challenges that the LiDAR design has. And maybe there other experts may have interesting approaches or interesting suggestions to give regarding the power management and things like that. And ways to approach the project, I think that maybe you are more capable of giving information about this than me. I know we have a web page, we have a social network accounts, and of course they can contact directly to myself or anyone involved in the project, and we will provide all the information they need and we are able to give.
All right. Okay. So to summarize, the main need of the project is to find more use cases, more potential use cases for
Sure,
such a
sure.
system.
Yes, this project is focused mainly in the development of the sensors. The three use cases are interesting, but they are there to show the potentiality of these sensors. And within that, these sensors have more potentiality beside these three use cases.
All right. All right. Okay. So then, if anyone has an interesting use case for this kind of systems in mind, please don't hesitate to reach out directly to me or Julio. You'll leave your contact details, and also on the RETINA webpage you can find all possible information for reaching out to our consortium. Well, with this, thank you, Julio, once again for a great summary. And
Thank you.
and we switch to one of the technologies you already mentioned, so the image sensors. And we have a researcher from IMEC, Carolina Blanche Perez del Notario, who will be the best person to introduce it. Hello, Carolina. Whenever you're ready.
Good afternoon. And yes, I'm just sharing it now. Can you see my slides?
Yes. Good.
Okay, perfect.
The floor is
So, thank you. So indeed, I'm going to present the work that we will do on chip spectral systems and also quantum dot-based imagers, as Julio already indicated. First, a quick slide just about IMEC. It's a research center in Belgium. By now, I think it's more than 4,000, like 5,000 employees. And basically, the focus is on nanoelectronics, digital technology. And here you can see a picture of the clean room where actually those spectral filters are being developed and deposited onto the wafers. But I will get to that. So maybe as a quick, maybe this could be basic for a lot of the public, but okay, just to recap. So what are we intending here with the spectral imagers? We are intending to increase the discrimination power with respect to regular color cameras. So in color cameras, we have three broad bands, red, green, and blue. And what we do with the spectral imagers is to actually divide these bands into multiple narrow bands and extend also to infrared and short wavelength infrared ranges. So beyond the visible. So when we get then instead of a 2D image, a 3D image, which means that for every point in the image, every pixel, we have the full spectrum. That is how the light is being either transmitted or reflected as a function of the wavelength. And this gives a very unique fingerprint of the material or the product, giving also chemical information. So then this, of course, we hope that then we will get more information on the viticulture cases or the medical imaging with respect to color imaging. So how is IMEC doing this? So IMEC has a different way. We call it on-chip, or developing the spectral filters directly monolithically on the wafers. So as opposed to traditional systems, spectral systems that were more based on some more complex for optics, making the system more, let's say, bulky and more expensive. So what is done as here is the filters are integrated, deposited directly onto the sensor images. So that allows them to have a more, let's say, miniaturized version. We can make the system more compact, as you see in the cameras here on the right bottom. Then it's more robust and it's also scalable because this is a mass producible technology. So this allows to then reduce the price. Makes it easier to integrate, and as Julio hinted, so because we can select for different pixels, for example, different kind of filters, we can acquire multiple wavelengths, multiple bands simultaneous, and this allows for what is called snapshot acquisition and video acquisition. So to deal with dynamic scenes like what we would have in, for example, surgical applications. And this can be patterned both on glass and silicon. So then one advantage is, as I said, that this is customizable. We can pattern, say, do the selection of how many bands are we depositing, which are these going to be, which are these bands. We can, for example, have sensors that have more like line scan systems, so they have typically contain hundreds of bands disposed as lines, and this requires a scanning movement. But then we have these snapshots, also called mosaic sensors, where we have actually some Bayer pattern. It can be 3 by 3 resulting into 9 bands, 4 by 4 to 16, or 5 by 5 to 25. So basically with that pattern, we can, like in color imaging, acquire the spectral bands simultaneously. And this allows to have, let's say, video capabilities. So what we have here is, for example, in the visible and near infrared range, they are based on CMV 2000 sensors. So we have invisible 460 to 600 and 2 versions in the near infrared from 600 to 850 and 975. And with patterns either with 4 by 4 or 5 by 5. So having 16 or 25 bands with up to 2 megapixels. So what we plan here is to do an upgrade of these sensors to get even higher SNR and higher spatial resolution, which might be required for some of these applications. This is an example here also in the suite range. So from 1000 to 1700 nanometers, we have these multispectral sensors. In this case, they are based on InGaAs sensors. And you have an example here of what is 3 by 3 layer disposition of the bands. And on the bottom, you can see the 9 bands that are simultaneously acquired, or you can show simultaneously the 9 bands. So as I said, this is very good for more dynamic applications where you need video acquisition. Then we are also working here on more novel sensors based on quantum dot based sensors. So these sensors consist of stacks of thin films. Those films are very thin with a thickness lower than the wavelengths targeted. And the advantage of these sensors is mainly that, so they have a higher pixel density, a higher spatial resolution is possible. So I didn't mention about the InGaAs sensors that I typically use, the spectral sensors I mentioned before, they are limited typically to VGA resolution, while in these sensors we can target a higher spatial resolution. Not only that, but also the lower cost of manufacturing has a potential, let's say, to have lower cost even of these sensors. So this would enable, let's say, the introduction in industry even further. So maybe then to show, so is the selection of this absorbent material of the quantum dot and some other tuning other parameters that allows to fix what is going to be the peak spectral response. So typically we have a strong absorption here also in the visible near infrared, but a filter can be placed here for this, let's say below 1000 nanometers, for example. And then depending on the materials that are chosen, so different lead sulfides here, we can tune this spectral response, spectral sensitivity. And of course, the idea is to do this like we use the other spectral sensors also as a way to know which are the most relevant wavelengths for the different applications, and that can drive then the development of the quantum dot-based sensors to select which are the most interesting peak wavelengths. Because here in these sensors, we aim to have maybe a couple of, let's say, bands, but it's, let's say, not aimed within this project is to have hundreds of bands. That's a more complex for this type of sensors. So also something that can be tuned is with the parameters. For example, we can push the efficiency, the quantum efficiency. In this case, for example, here there was some tuning of parameters to shift a little bit in the wavelength, but then increase further the quantum efficiency. And of course, to test these sensors, we need also some kind of prototype camera, modular cameras, where we have some adjustable electronics, and it's very easy to replace one sensor version, so with some big spectral response or another of the different quantum dot-based varieties we have. So as a baseline, we have the one with a focus on 1,400 nanometers, but then we also have reductions on 1,200, 1,550. So depending on which bands are the most resulting more interesting for the different application cases and others under development. And in terms then again of pixel density and spatial resolution, we start with a baseline that has 5 micron pitch, but we also have some alternatives with a higher pixel density and then increasing the resolution considerably with respect to what is the typical VGA. So here's also an image taken, and you can see it's quite a nice spatial resolution for this type of sensors. So this will be introduced later more for the application cases, and also Julio mentioned it. So the idea is to use, for example, in the medical use case for this surgical application. So we want to have a video acquisition. That's why then those snapshot 3 images here, and together with the LiDAR also coming from another work package, to integrate them all into a multi-sensor camera system. So that will have, as Julio mentioned, so it's high resolution RGB cameras, also linear sensors, and these sphere spectral sensors. So the idea is then to combine multiple sensors here with a beam splitter and to be able to capture at a video rate different bands in different ranges, together with also the LiDAR complementary information. And here Rizal from from QMI, they will go more into this detail, the kind of application cases they want to target. Similarly, for the viticulture case, we're planning to use the developed sensors in the visible and infrared range, and these will actually be integrated into low power smart spectral camera prototypes by photon focus. The idea here is to, as Julio mentioned, to have a ground-based system, so more the camera at a distance close range, 1 meter or so from the plant, but also drone-based systems. So in this case, it's also very good to have the snapshot systems for this kind of drone acquisition. And of course, here also we are planning to use the quantum dot-based and take as an input, which are the most relevant wavelengths selected to select that development, let's say, for the quantum dot-based cameras. And I think that was all. Maybe I went too fast. So you can, of course, have some questions now, and also for later after the meeting, if you need more questions or you have more information required on chip spectral images, you can contact Wouter Charlie, that is our program manager, or myself. And actually for thin film quantum dot-based images, that would be Paweł Malinowski from IMEC. That is also a part of the RETINA project. So thank you very much.
Okay, thank you very much, Carolina. Nice presentation, and yeah, very exciting developments happening at IMEC as always. I'm wondering, so the key element of these images is, of course, the quantum dots. Are they chemically synthesized inside IMEC, or you use commercial quantum dots?
So that more as a kind of lab, more artisanal base. So for example, that's not transferred yet to production, let's say, at the clean room. That's something, that's some step that would happen later. So, but then more, this would be a more a question, I think, for Paweł.
All right, I see. So, well, maybe either this key element or any other elements of the images is something that where you can also benefit from external partners. Is there something that IMEC can might need in these developments?
Well, here it's of course interesting, as Julio mentioned, also input from, since we are using the input of these application cases, right, to direct a bit the development in terms of which bands also, and what number of bands can be more interested, what are the requirements on the spatial resolution. So all that is some input that is very valuable to know how to direct, indeed, for example, the quantum dot-based development. So all that kind of information would be always useful and welcome.
Okay, yeah, fair enough. Is there any further questions from the public? Okay. If not, I suggest we thank Carolina again for introducing the topic. And we have a great speaker to catch up on this. And it's Peter Mario Schwieder, the CTO of Photon Focus. And I think Peter will continue the story of the imagers and sensors. Thank you, Peter. Floor is yours.
So, hello again. Yeah, here's Peter and Carsten from Photon Focus. We want to give you some insights about our role in the RETINA project. Our contribution to the project is our experience in hyperspectral imaging camera design and our experience in embedded cameras for drone systems. You see here one application we have solved with our cameras in vineyards. It's a drone inspection for mostly let's say water content in the fields. Yeah. So Photon Focus is part of Atlas Copco Group now, and the Atlas Copco Group has 4 big business units, and we belonging to industrial technique. And in this industrial technique business unit, there is one big solution for machine vision, the machine vision solution. You know, maybe ISRA Vision in Germany, and we belonging to ISRA Vision and around or with additional, let's say, companies. ISRA Vision is the core of the new machine vision business unit. Our background is more than 20 years CMOS sensor and camera design. So we are pioneers in the high performance CMOS imaging, and we manufacture since 2001 several sensors, and our main focus are modular camera designs, which are used in many industries, not only machine vision, also in the metrology, sport, food, and railway inspection. So ISRA Vision itself has around 1,200 employees and working on machine vision system solution, is one of the biggest machine vision solution vendors in Germany. And we have here in our group over 10,000 installations worldwide. And I think Atlas Copco you may know from the street, from the compressed air, and there are some over 50,000 employees, and a lot of fields are covered by our group. So the Photon Focus products, we have 8 main families, starting from line sensors to high-speed sensors, high-resolution cameras, a lot of 3D camera cores and OEM solution, but also we cover with our camera with the photon spectral series, we cover a lot of hyperspectral applications, sphere applications, and also UV applications. So we have not only hyperspectral cameras there with the snapshot sensors of IMEC, we have also implemented sphere sensors for push-broom applications, and we have also bringing a very interesting solution which can deal deep UV, and this is also used in hyperspectral imaging. We are working in we call this Lego stone systems. So we have several camera platforms, smaller ones, and was two small platforms, the MV0 and MV2, are dedicated to sensors which have maximum 16 LVDS channels. So even if the camera is really small, the cameras are really fast. We have huge FPGA resources for real-time image processing. And in this platform, we implemented snapshot images from iMac, and a very special product we have implemented is a so-called drone box. It's a box which containing two hyperspectral imaging cameras, one in visible and one in near infrared. And all the data are collected in a PC-based system together with a high-precision GPS navigation module. Cameras are really small, so we have one option to go 30 by 30 millimeter form factor, and we have a bit larger one with a better cooling, 40 by 40. And in addition, we offer the OEM modules, so the PCB stack only, and the PCB form factor is 26.5 by 26.5. So very compact, very fast, and a lot of FPGA resources make it really comfortable in applications where size is an issue. Then we have another platform which is dedicated for sphere sensors. So often the sphere sensors are analog sensors, and we built up here an extra platform to implement cooled sphere sensors based on indium gallium arsenide. So these cameras are mostly used together with spectrometers in so-called push-boom applications. And here we implemented a complete shaft coder interface to support this push-boom applications. So we have several standards here for shaft encoder interfaces, which could be selected by software. And in addition of all this, let's say, hardware, we have a lot of firmware available, for instance, to make operation corrections and other pre-processing steps for the spectral data. Then we have another platform for the digital world. So we have a high-speed platform for demanding CMOS sensors with even higher FPGA resources. So the focus is here really pre-processing to sort out all information which is not needed to avoid that we need a large bandwidth to the host PC. So most of the data are sorted out on the camera head as a special implementation. I show you later a dual aperture camera we realized in the multiple project. And the form factor of these cameras is mainly 60 by 60 millimeters, but we also sell for our partners the PCBs with also a demanding form factor of 46 by 46 millimeters. In our last project, European project, we implemented a dual aperture camera. with 2 sensors with snapshot filters manufactured by IMEC. The top sensor you see a sphere sensor with patterning, and in the bottom you see the CMD 2000 hyperspectral sensor or the version. And we implemented here mechanical shutters for calibration of the cameras, and we, by luck, both sensors have the same speed, the same readout speed, so we could merge the 2 images into one image.
Hörst du mich jetzt noch? Okay, okay, so hat's gelöst. Ja.
Okay. Yeah, so together with this, I gave you more the technical drawings here, that you see more the inside. So it's not only the implementation of the PCBs, also improved cooling structures to really cool the sensors, for instance, especially the sphere sensor. And the transmission of the data was done here with a 10 gigabit Ethernet to have really the full speed and to give the customer the benefit to go with a high frame rate into the inspection system. In the RETINA project, we have a bit another focus. So the main focus is to reduce the power consumption of the solutions and to implement a high performance AI platform for drone-based hyperspectral imaging systems. So we know from our experience with drones that power consumption is a big issue. So we focus here on several points to reduce the power of this hardware. But in addition, we focus here also on an embedded part to use very low power, high performance AI processors to solve the application or the use case in the vineyard. Yeah. So this is our main focus.
Okay,
Question?
thank you, Peter. Is this the last slide?
Yes.
Okay, good. Thank you very much. Nice introduction of your cameras. Actually, I'm wondering, actually, is this really a state-of-the-art camera or something innovative and some elements of it are really developed for the first time?
Yeah, first time it's the focus on really low power is demanding. So we're trying to really looking for many components to reduce the power. It's not only to focus on the next version of image sensor. So the power consumption starting already there on the first PCB of a camera, but also we focus on the processor platforms. So we go 2 approaches there. We implementing low power FPGAs or ultra low power FPGAs, and a really new approach is to go for embedded processors with AI accelerators. There are many on the market, but there are also not so much which are low power. And the benefit is here really or the goal is to try to use these low power devices for the drone business. We think this should be feasible, but end of the day, we have to test this together with the colleagues which makes the software. But we think it's working, and the other step is we are working on very new technology to reduce the power of the physical layers. And there we have the first results here. It's getting really good that we can reduce the power of the interface from 3.5 watt to 1 watt. Yeah, which is really remarkable. And these are brand new physical layers on the market, so they are still engineering samples or in the introduction phase. So it's really brand new, and we're working here on the IPs and the PCB solutions to make this available for the customers and also for the RETINA project.
Okay, I see. And another question is, can you foresee using the same kind of low power camera and a drone based for other applications, such as, for example, search for minerals or forest fires?
Yes, for sure, there are a lot or a high demand in other industries. We have one application which is completely different. It's a mining application where we have an open pit, and there is a question sorting out copper ores. And there's a very good spectral signature between copper oxide and copper sulfide. Yeah, and the problem is here that the preparation of the metals has two passes, two chemical passes. One is an oxygen pass and one is a sulfur pass. Yeah. And if you put the wrong ore in the chemistry, then you kill the chemistry. So the goal is here, right, to fly with drones in the open pit and to sort out the materials already in the pit. Yeah, that's the right material is coming to the preparation lines. Yeah, that the chemicals are really secure, that you don't kill the preparation of the metal later. Yeah, is what you see. Yeah, drones coming more and more, also in other applications. For instance, stone industry. Yeah, and before some geologists had to climb the mountains and to see what is really on the wall of the
cliff.
Yeah, and now you can really go by a drone and a spectrometer and make the measurements with much less effort. You are much more precise, and I think this is also accelerating these industries, but also it's very interesting from the environmental standpoint, because you avoid a lot of issues later in preparation of all the materials.
Okay. Yeah, indeed, there's a lot of exciting applications that come to mind. And yeah, as mentioned by our first speaker, so the project is welcoming anyone who can think of an interesting use for this camera in particular, so to reach out to us. And so with this, I'd like to thank Peter again for a great presentation. And I pass the word to our next speaker, Francisco Luz Suarez. He's a researcher of University of Vigo, who will tell us more about the LiDAR and the photonic integrated circuit part of the project. Francisco, are you with us?
Yes, I'm here.
Okay, great. So then just put your slides in the full screen mode, and the floor is yours.
Thank you very much. Yeah, we're going to now change a bit the topic now. It's going to be a bit more physical layer, perhaps not the technology that's not as mature as the one from IMEC or Photon Focus, but where we have high hopes that it will be a good technology and can be very beneficial. So the topic is going to be integration of FMCW LiDAR picks on indium phosphide technology. I'm Francisco Suarez. I am actually the CTO of a newly founded foundry here in Spain in the University of Vigo called Spark Foundry. But I also act as an associated researcher at the University of Vigo. So I'm here on behalf of the University of Vigo to present this work. As of first, let me introduce you to the Coffee Lab. So we're at the University of Vigo, and we are part of the Coffee Lab group of the University of Vigo, and where we've already have a spin-off, which is the Spark Foundry SL, that is a spin-off from the University of Vigo and specifically from the Coffee Lab group. And we focus on mainly on developing chips, on photonic integration and on integrated photonics. So developing all kinds of chips on different materials, different wavelength ranges for specific applications. We have several projects of which we mention here below. RETINA, for instance, where we're developing FMCW LiDAR chip. We also have a Marie Curie project where we're developing all kinds of chips for satellite communications. And we recently started a Spanish project called Next Chip, where we're developing more design and characterization techniques for photonic integrated circuits, and where we'll also offer an intense training on the design and development of photonic integrated circuits, from chip design to fabrication, testing, packaging, RF design, and also some other, and also quantum. So if you guys are interested, yeah, just please get in, visit our website, which is from the University of Vigo. So the Coffee Lab, it's coffee.eu, and you can see there when this will be coming up. This is a bit our team. So we've got our group leader, which is Francisco Diaz-Otero, and we have lab manager and Miguel Carbonell, and a professor at University of Vigo, Francisco Javier Fraile, and myself as an associated researcher. And we've got here several groups that are working on mainly three topics: sensing, optical communication, and quantum. And yes, this was a short introduction to our group. Now we move on to the actual work here in the RETINA project, and there we come to this FMCW LiDAR principle. So the FMCW is a photonic way to determine, using optics to determine the distance of objects to get a 3D cloud. And there are many different ways of doing this. The most commercial one, which is, for instance, what you see on the iPhones, that is based on time of flight LiDAR, where you send a pulse and then you measure the time that the pulse has been reflected back, and there you can determine the distance of objects. And if you send the pulse towards all different directions, then you can get these multiple points. There is actually another approach which has several advantages, and that's the FMCW LiDAR approach, and that is what we will be developing here in RETINA project. So in the FMCW LiDAR, that is basically what's called a delay line interferometer. Well, if you're used to a bit chip design, then when you say delay line interferometer, you know that it's basically a Mach-Zehnder interferometer, or let's say a modulator. However, one arm is very big, is much bigger than the other, and this will result in a frequency wavelength. When you change the laser wavelength, it's going to oscillate. And when these delay line interferometers, they're commonly used on the in chips, where if you want to do, let's say, a wavelength filter, then you typically use them. But on a chip, these delay lines, this longer path is usually, let's say, a couple of millimeters. So that means that you have the wavelength filtering due to these oscillations is going to be like a couple of nanometers. However, in a LiDAR, you have, of course, that this length is much longer. And that is the length that, so in a LiDAR, the light goes out of the chip, reflects off the target, comes back, and then is detected by the balance detector. And there you will have since the lengths are much longer, then this filter is going to be very narrow, that you get filters that are inside of the wavelength, inside of the electrical frequencies. So you see here for 1 meter, this ripple in the wavelength is going to be equivalent to 150 megahertz and so on. And I'm sorry. This is how much of the tunable laser, the frequency that you need to tune in the tunable laser to get a frequency signal here at the balance detector. And so for a distance of 100 meters, this laser needs to be only tuned by 1.5 megahertz, which is like a very small change in the optical wavelength of this tunable laser. And as the distance gets shorter, then it's going to be higher. So this is basically the FMCW LiDAR concept. So you have a tunable laser that is going to change the wavelength according to these ranges up and down. And then the light goes, a part of it stays on chip, the rest goes to the target, and you use the balance detector to measure the signals that you will get. And this signal at the balance detector is sampled, and you do basically a Fourier transform, and then a Fourier transform, or you could also put on an electrical spectrum analyzer. And then you start to get this frequency. You see here on the frequency, this is a simulation, by the way, from BPI Photonics. When you measure this balance detector and you put on a frequency on an electrical spectrum analyzer, you start to see these peaks, meaning that the signal that you have measured has got this frequency component. And you see here this for different distances. And the location of this peak is going to tell you where your target, what is the distance to your target. You need to take into account several factors like the sampling rate and also the speed at which you change this wavelength rate, which is the chirp. It's called chirp. Well, a lot of people call it chirp, but so based on that, on this information, you can then retrieve the signal. In addition, if the target's moving, then if you see here the change in the wavelength of the laser, when it goes up and it comes down, at this upwards flank, you'll get a peak here, which is off the center of a non-moving target. And when the frequency goes down, you get another signal there. So you will see then two peaks in your electrical spectrum analyzer, and that means that your target's moving. And this is basically the FMCW LiDAR, which, as I mentioned, has several advantages over time of flight, which is that less laser power is required. Basically here, in the balance detector, you're measuring relatively small signals, so they're going to be mainly, let's say, in the noise. However, due to the interference, you will be able to see them on the spectrum analyzer. So typically you need less power required than for a time of flight LiDAR, because on a time of flight LiDAR, since you don't have this coherence, you're not interfering the local oscillator with the signal coming from the target. So this signal that you're getting, it needs to be above the noise level of your detector so that you can detect it. So you need to increase the power a lot so that you're at least above the noise level, which can be sometimes even, let's say, if you're on a bright sunny day, then you're getting also all that light that's going to cause interference on your detection. So that's going to cause disrupt your detection. So that's something we will not have here with FMCW LiDAR principle. Due to the interference, the coherent nature of this LiDAR, we don't have interference from other light sources, including the sun. As mentioned earlier, we can simultaneously measure the target distance and velocity in one measurement, because when we're looking at our electrical spectrum analyzer here at the balance detector, if we see two peaks, then we know that the target's moving, and the distance between these two peaks is going to tell you also the velocity of the signal. So this is basically the concepts of the LiDAR. And then how can we start to translate this concept into an integrated chip? We've got here this concept, and if we fold this balance detector and then we come to this structure where we would need to have a collimating lens to transmit the light to the target. And then the light's coming back and we're going to detect it here in the balance detector. And this is one way of integrating a LiDAR also on a chip. And however, another way, and this is what we're going to do in this project, in the RETINA project, that is to use grating couplers. So as you guys perhaps know, the grating couplers are devices, is a grating that has a period where such that the light is transmitted off the chip. And by changing the wavelength of the light, you can change the angle that the light is transmitted. So this is basically the approach that we're going to go for in this in the RETINA project. And specifically, the type of chip that we are looking for, will be more towards the end of the project. We will be developing a chip. The goal of the RETINA is to develop a chip, a single chip with an integrated lens that will act as a LiDAR pick. You see here the schematic a bit. This is just the initial designs of the chip, where we have a tunable laser we have here power divider, and it goes to a grating couplers, and then the light is transmitted towards the bottom to the targets, coming back and received at the same grating coupler, and then we can use here the balance detector to detect the signals. And in this case, the advantage of this setup is we can also send multiple beams simultaneously that go towards different directions. We can see here a slide of the ZMAX simulation that shows how the light is focused through this cylindrical lens, where you can see that the light's coming from different directions is going to focus on different gratings and due to reciprocity. So when you transmit the signal, it is also going to go towards the same direction. So with this concept, we can achieve, so along the x direction, so that's along the direction of this the chip of these grating couplers, by changing the tunable laser, the wavelength of the tunable laser, we can transmit the light towards different directions along the x, along the grating couplers. And simultaneously, we're transmitting multiple signals towards multiple angles along the z direction, so perpendicular to the gratings. And yes, this is basically the concept that we are aiming for in the RETINA project. This is one architecture, one of the architectures that we're studying, even though we're also investigating others where we'll have multiple gratings here to capture the light that comes a bit adjacent to it. And also we're investigating coupling light from two directions so that we can have even more simultaneous beams coming out. And yes, so the technology that we will use to realize this chip is the technology already developed by Fraunhofer HHI, which they offer currently multi-project wafer runs. And in this technology, we already have the tunable lasers. They're already developed, albeit for low speeds. We're trying to increase the speed of the tunable laser, but we already have this network of waveguides that can be easily achieved. And they also have the balance detector. So this technology already has all these components. They're already developed. What we need to do in the project, and that's the goal of the project, to develop these grating couplers and to develop the cylindrical lens. You see here a picture of an example of a picture from the HHI technology, where you can see here that we have detectors, can be photodetectors or balanced photodetectors, all types of straight waveguides, wavelength filters, lasers also. We see here an example of a DBR laser. And this would be a bit the type of chip that we are developing here in the RETINA project, based on the technology of HHI. And together with HHI, we will develop these components. And we will also use the assistance of IMAN to develop the electronic circuitry, which is mentioned here, the electronic signal processing, not only for the balance detector, but also these electrical drive currents and this sampling of the balance detector and the post-processing that will be done by IMAN, as Julio had mentioned earlier. So and this will be my final slide. So this was just a brief overview of what we are targeting in retina, and also an explanation, well, at least according to our understanding, how a FMCW LiDAR chip works. So what we are addressing here in retina is due to the fact that there is already an existing HHI MPW platform. We are adding grating couplers and micro lenses on the existing HHI MPW platform. And after we have done that, then we will design the LiDAR peaks that to meet the requirements defined by the application partners, by the application partners that we will soon, you guys will see in the next presentation, which include the long-range LiDAR and the short-range, the long-range LiDAR for mainly automotive applications, and a short-range LiDAR mainly for the medical application. Yeah, this is a bit a quick overview. If you have any questions, just let me know.
Thank you very much, Francisco. Yeah, seems like you're aiming to solve one of the key challenges of the photonic integrated circuits. So this is a great mission.
Exactly. Yes, we hope that if we're successful, that this is going to have many applications. But let's see.
Right. Fingers crossed.
Fingers crossed.
Promising though. I think yeah, you already get some questions in the chat. Maybe let them ask it aloud. Mercedes from TNO, would you like to unmute and ask your question?
Yeah, basically I did ask already on the chat. Basically, what are the challenges from MNCW LiDAR? Because it seems that it's better than other options, but still, I'm sure there will be some issues. So if you could comment on that.
Well, mainly the issue is the coherence to get in the past. Let's say if you look, let's say at the the commercial LiDARs, they are typically time of flight, and that is mainly due to the to get this coherence. It is quite complicated because if you this coherence basically it limits you to do everything on a chip, because if you have to have several chips and you need the coherence, then the phase of the light needs to be very well precise, and these separate chips, they cannot move. Otherwise, you lose the coherence or you introduce some oscillations on your signal. So that's why the time of flight LiDAR, where you have one chip that is a light source, and where you have an array of sensors, there you don't have any coherence, but your system is a bit more flexible. It's more, yeah, you cannot. It's not susceptible to vibrations. However, if you can integrate everything on a chip, then you can solve this, then you can have a fully coherent system, and you can achieve FMCW LiDAR.
Okay.
Okay, I hope that answers the question.
Yeah. Sure.
Okay. Well, thank you, Mercedes. There's another question.
Yeah, sorry, there were another one, is how you will solve, because in FMCW LiDAR, you can detect if it's moving closer or further away, but if you move towards the side, I mean, you don't see anything getting closer or farther, it's just the same distance.
Well, yeah, it's the same distance, but you will take it, of course, several snapshots, right? That you will see in multiple snapshots. If you take multiple snapshots, then you see that your target's moving to the side. However, if it's moving farther away, but it can also be diagonally, because a diagonal movement, you can also see that. So if it's moving, let's say, diagonally or away from you, towards you, with one single shot, with one single snapshot, you can determine the velocity. But if it's staying at the same distance but moving to side, then you have to use multiple snapshots.
Okay. Thank you.
You're welcome.
All right, and another question from the chat was about the size of the indium phosphide substrate that you use.
Well, the indium phosphide substrate, so the technology of HHI currently, they start working with 650 micrometers on a 3-inch technology. The thickness of the indium phosphide chip will be determined actually by us, because, you know, since we have to design these micro lenses, the distance from the top where the waveguides are located to the lens is very important, and that is a very important design parameter for this for the curvature of this micro lens. And typically we want to have, so this is basically the focal length. This is basically the focal length of this micro lens. So currently we're aiming for a focal length of around between 500 and 600 micrometers. So that means from here all the way to the down there, you will have 500 to 600 micrometers. And there are several things to consider here, but we'll have to have a look at this. Because as you know, this waveguide width, the spot size here, is going to determine the divergence of the light going down. But since indium phosphide has a high refractive index and the divergence angle depends on the refractive index, so you're going to have a reduced divergence angle, and that is something that we will have to take into account as well.
Okay. Well, thank you, Francisco. I think we need to catch up with time, but thanks for the presentation. And
welcome.
I invite now our next speaker, Rick Pijsen, Senior System Engineer from Xinematics. We'll open up the parts on the applications. Yeah, please, Rick, share your slides, and the floor is yours.
Yeah, let me know if you can see it.
Yes, all good.
Okay, so good afternoon, everybody. My name is Rick Pijsen from Xinematics, and I will be introducing Xinematics into the RETINA project. So first of all, who are we? Xinematics, we are a company based in Belgium, in Leuven, near IMEC, by the way. So, but not at all, not connected to IMEC, apart from through the RETINA project. We were founded in 2013 by private investors, and so we've grown up to 45 people today. Yeah, we worked primarily on solid-state LiDAR technology, and in this context, we have built a patent portfolio of more than 80 patents. We are present across the world, as you can see on the map here. So again, green dot headquarters in Belgium, Leuven, but we are represented in almost all continents through local offices and resellers. So what do we do? What are the markets we serve? You see three pillars. One is road construction and maintenance. On the left, so this is a technology that we've worked on to gather data on road quality and generate digital twins for roads, mainly with the purpose of helping, let's say, governments, local governments, and road construction companies to decide, okay, what's the next best spot to improve the road quality, given there's some deterioration over time. So that's let's say column A. Then in the middle we have the industrial pillar, which is mainly related to industrial LiDAR, working in mining area, for instance. You see here this picture of this big Caterpillar dump truck, and that's an example of one of the projects we've been working on with industrial LiDAR. And then the third pillar is the automotive category, where we basically try to leverage the knowledge we have on LiDAR technology to work towards the use case, which is also a part of the RETINA project here, being the assisted driving use case. Yeah. So how do we contribute here, or let's say how do we get to this? This is related to our product portfolio called XenoLiDAR. Yeah? And as I said in the beginning slide, we have been focusing since the beginning of Xinematics on true solid-state LiDAR. We call ourselves the pioneers of true solid-state LiDAR, especially in considering long-range LiDAR. Compared to sometimes you hear competitors saying, okay, we are true solid state, but if you then really look into it, there's always some kind of scanning mechanism. We even consider MEMS scanning not to be true solid state, because in the end, there's something moving inside. Yeah? So over a decade, we have experience in LiDAR development from the core technology up to full systems. And we have been working with various automotive customers for integration projects, for instance. You see on the right, there's a little overview of projects we've been working on together with Marelli, working on a wide field of view through solid-state LiDAR, and you see it because of the combination of, let's say, all subsystems, allowing us to look very wide and at the same time very long in the middle of the field of view. So that was one of the examples where we've been working in the automotive context with LiDAR technology. There's also windshield integration, and here you see there's a LiDAR in the headlamp. Also example integration projects. What's important here is to have an idea of or to understand the interaction of the LiDAR with the windshield in this case. You can imagine a very shallow angle of incidence to pass through a windshield, and on top of that, typically a windshield has some kind of a layer inside that absorbs or even reflects near infrared, which is exactly the wavelength that LiDAR typically works in. So these kind of integration projects has given us a lot of insight on how to integrate such LiDAR in automotive context. Also, usually automotive customers, they don't want to have LiDAR sticking out, they want to have it neatly integrated. But then, of course, you have to deal with all these optical consequences, like the windshield, or also like the headlamp, where you typically also have like a curved cover, usually polycarbonate, not well controlled in thickness, etc. So there you can also have various optical effects interfering with the performance of the LiDAR. So let's say we have a bit of a track record here in the automotive sector. So, and that's also why we are part of the RETINA project. Let's say as a step towards monetizing the development inside in RETINA. So, in the first place, we will represent the end user for the ADAS use case to define the LiDAR requirements. Referring here to system requirements for function and integration, function being related to the range, the field of view, these very basic parameters of a LiDAR, all the way up to integration, what is required to make it automotive grade, temperature range, fail-safe mechanisms, etc. So that's the first point where we will contribute in the project. Second point is we will assist in developing AI algorithms, machine learning, to process LiDAR data in conjunction with visual camera data for the use case. And this is partially reusing, say, what has been done on visual cameras, but mainly seeing how we can reuse this and make it better using the LiDAR being developed in this project. Examples for these algorithms are like road user detection, classification, and eventually also tracking to predict what's surrounding road users are going to do to avoid collisions. And of course, ideally, we can do this independent of the weather conditions. And a third point where we can assist, we have quite some experience in the past years of fundamental LiDAR testing, like testing the fundamental performance, again, range and noise levels, see how this relates to what you expect, see whether we are at the limit of what the technology can physically do. So also that is where we will assist in this project. Defining the LiDAR, so Francisco just introduced the core technology, but of course he needs some input on what should the technology do to support in the end the use case. So here is an overview of information that we've gathered over the past years through interactions with leading tier ones and OEMs in the automotive world. And this is basically a hot list or a top list of the fundamental requirements like resolution, range, field of view. Then what you typically, if you start, I will not go into detail, but if you look at the numbers, you will see that many variables are all over the place. They range, for instance, resolution from 0.05 degree, which is close to what you have in a camera, up to 0.5 degree resolution. All of this depends, of course, on all the other parameters, like what is the range. If the range is not that big, of course, you don't need that much resolution, etc. So, but we have an overview of various requirements, and we have, from this we deduced basically the ideal LiDAR for the application. So this input has been used to define, in this case, two variants of a LiDAR, based on which Francisco and the team started working on the big chips for the long range LiDAR. Another topic we've been working on up to now is the AI development. So we made, let's say, the first steps here. What you see here is, of course, not yet any machine learning or AI algorithms. This is just a starting point where we gathered some data of an RGB camera and external LiDAR in this case. So you see that we can augment the data. We can augment the LiDAR data with color data, and also we use the 3D information to give some kind of a bird's eye view of the scene that you see here. It's a crossroad. You see pedestrians, bicycles, cars, vans, trucks passing by. And the idea is basically to use this kind of data sets as a starting point to start developing the algorithms. And the first point would be the annotation of the data. And together with one of the partners, Abaya, in the project here, we will set up an environment to do data annotation, which we can then later on use for doing the training of the AI algorithms. And the idea is, of course, to have everything in place such that by the time the big LiDAR is ready, and will generate data, that we can plug in this data into this platform, and it should be a straightforward way to work towards the new AI algorithms. So a very top level introduction of what we will be doing in this project. That was what I wanted to present here. So thank you for listening, and if you have any questions, okay, I'm happy to answer them.
Thank you, Rick. Great presentation, and yeah, indeed, you're one of the key partners inside the project, because you can tell actually the well, everyone who's developing the LiDAR parts what is actually needed, and actually coming back to those specifications that you get from the key tier one suppliers for automotive, for example. So is there one key parameter that they all maybe stress the attention on?
Yeah, it's usually the combination of range and resolution that matters the most. The range above 150 meter is typically what is needed, especially for highway driving. But of course, if you want to look that far away, you have to have good resolution to be able to distinguish different objects. So that's one of the, it's always in groups of two, of course. So I would say that is the top level requirement.
Okay, okay. And there's similar things for the drone application as well?
Drone application, not so much aware of. I would say the range is there less of an issue. Going that high, flying up to 150 meters. I think they're more the field of view and the data rate matter the most, to have as much as possible data throughput and scan as much as possible area in a short time, let's say within the battery lifetime of a drone.
All right, all right. So is there anything particular that you might need from the external partners and from all the value chain of photonics and sensors represented here at the meeting?
That's a good question. So of course we rely on the partners. I just mentioned the Ambraya platform, which will be very useful for the AI for the annotation, for the AI development. And of course, we also rely on Ayman to provide us with the interface between the.
Sorry, I imply the people who are not the partners of the project.
Okay.
Someone who's watching us and maybe can reach out to you to help you with the developments.
Yeah, okay. It's I didn't think of this question. I cannot answer it on the moment. But if anyone has ideas to contribute in this project, I would say reach out to us.
Okay. No, that sounds good. So I think you summarized very well also your part. So with this, I'd like to thank you, and I give the word to the next speaker, who is Rachel Hovling, the manager for molecular and fluorescent imaging innovations at Quest Medical Imaging. Hello, Rachel. Okay.
Hi, Ivan. Yeah, sorry, the system is a little bit slow, but I will share my screen.
Perfect. Okay.
Yes, there
we
we go. Perfect. Well, thank you everyone for joining the workshop today. Again, thank you. I will present the company that I work for, Quest Medical Imaging, and a part of the work that we will doing for the RETINA project. Quest Medical Imaging is a company in the Netherlands, located in Wieringerwerf, and a little bit in the northwest, above Amsterdam, for those who know a little bit the geographics of the Netherlands. And since a few years, we have been acquired by Olympus. So we are now part of the Olympus group, and but still continuing to develop and produce our medical fluorescence imaging systems. And this is the example of one of these systems. Yeah, there we go. Oh, yeah. So what you see here on the right is our Quest Spectrum. This system is able to provide the surgeons information about near-infrared fluorescence, so fluorescent light that is not visible with the naked eye, but can be acquired using this camera. And what we do is acquire a color image and a fluorescence image at the same time to make navigation easier for the surgeon. Here you see the principle behind it. So with normal white light that we shine on the tissue, you will obtain a normal color image, so the RGB. But once we start by introducing a laser, there we have the excitation of the fluorophore that can be injected into the blood. And then we have the NIR image that is created. Then additionally, what we do is add the overlay images. So this is a combination of the color and the near infrared image. This is the typical green overlay that is known for fluorescence imaging. And what we also do is adding a false color impression of the intensities measured by the grayscale sensor to give more discrimination between high levels of fluorescence and lower levels. And with our camera, we are able to not only acquire one color image and one NIR image, but also have a second NIR fluorescence camera inside, allowing us to obtain information about two different fluorophores. The typical fluorophore that we image is the indocyanine green. This is also the fluorophore that is used the most and can be visualized by most fluorescence imaging systems that are available in the market. However, our system is able to also see other fluorophores that are under development or are used for different applications, like methylene blue. This is an example of the use of fluorescence in vivo. So what you see is the detection of the sentinel lymph node. What the surgeon does is inject this fluorophore in the region where a tumor is located. And based on the draining of the lymphatics, the first sentinel node can be found and detected, which is important to be investigated by pathology to detect whether there are any metastases located in that sentinel node. This may give information on how to treat the patient and how far the tumor has spread already. Another application is using it for the assessment of perfusion. So after injection of this fluorophore, the intensity of the fluorescence and the fluorophore traveling through the body can be measured with the camera. And what you see is then a change over time. So you have the inflow and outflow of this fluorophore in the tissue, and this will give you potentially an answer on how well the tissue is perfused. Here you see some examples also from literature and from our partners in the project. For example, for the colon perfusion on the left, they use this to assess whether anastomoses are created in a right way. For breast reconstruction, tissue is collected from another part of the body and then recreated into breast tissue. And what you want to reassure as a plastic surgeon is that the tissue that you transplant, that it is viable for this reconstruction. And also assessment of how well feet are perfused is done using a similar application of the injection of ICG. And based on this, also different types of vascular problems can be assessed. Another way to use fluorescence imaging in a medical setting is using fluorophores that can target tissue. So the examples that you've seen are the non-targeting fluorophores. So these are dyes that can be injected into the human body, and they fluoresce because they go with the flow, literally. They move through your blood vessels or through your lymphatic vessels, and just show you where flow is happening and where different blood vessels are going. However, there are many initiatives to develop targeting probes. So these probes can attach to different types of tissue. An example is tumor tissue, where you can have, for example, an antibody labeling, a peptide labeling, or a small molecule labeling. They are looking for their connection in the tissue of interest. So, for example, tumor tissue, and they will attach to the tumors. When they are not attaching, they will be excreted from the body, and after a few hours not be visible anymore. But the ones that have been targeting and have been attaching to the tumor cells will be able to be visualized during the surgery. Typically this type of dyes would be injected before surgery, and then literally highlighting the tumor cells of interest. And other fluorophores are smart activatable and pH activatable probes. I will show you an example of one of the targeting fluorophores that has been used recently, and also has been approved as one of the first targeting molecules in the field. And this is on target probe. So this is OTL38. It has been FDA approved recently, and is now the first to be used for the detection of tumors. An example that you can see here is where the fluorescence is showing where the tumor cells are, and based on this information, the surgeon is able to dissect this tissue, and also investigate whether all the tumor tissue has been resected after they made the first resection. Another application that we work on mostly in research is the spectral imaging, especially in the RETINA project. We will work again on spectral imaging for detection of the intrinsic chromophores that are present in the body. So different than the ones that we inject with the fluorescence. You have the spectral information that is already in the body itself. And we have experience with different types of spectral imagers, and we have integrated multiple into different cameras for specific research. And our goal is to, as real time as possible, create images with more information than just the RGB that we get with a normal photo camera. And here you see an overview of all the different types of cameras that are available. But of course, we will try to develop an even better one in the RETINA project. And one of the examples of the spectral imaging that we have, spectral imaging cameras that we have created in another project is the multispectral snapshot camera, where we integrated two different IMAX sensors and an RGB camera to assess the oxygenation of tissue. And in this trial that was done, also the comparison was done to the laser speckle imaging to see if we were able to see the same effects in the oxygenation as we would see for the laser speckle imaging for the perfusion. Our role in RETINA is a little bit a combination of what we are working on a daily basis. So we will focus on the healthcare use case, where we are investigating the user needs and requirements. We've had already extensive meetings with the medical partners in the project to assess what needs and requirements would be specifically for the RETINA use case. But on top of that, we will be we will also integrate our knowledge that we have already obtained with our medical devices in the field. Additionally, we will provide test data and phantom material for the initial testing of the algorithms and further development. And additionally, we will be putting together the demonstrator for the medical use case, and where we will investigate the user needs that have been identified. Three of the most important ones are that we want to decrease the background signal and optimize the penetration depth for the fluorescence imaging so that we can see deeper in the tissue and have better contrast from the fluorophores compared to the rest of the tissue. And on top of that, we want to see if a 3D structure can give us additional information for annotation and processing compared to a 2D image. What we will integrate is here, is part of this bigger overview where you see all the technologies that will be integrated in the RETINA project. And what we will do is use the LiDAR sensor for the 3D imaging and the IMEC spectral snapshot sensors to be integrated into our prism-based camera insights, where we will be able to do the visualization of both the color image and the spectral information at the same time. Besides that, we will work on the data analysis and further development of the machine learning and new applications that can be developed using the information obtained with the sensors. And we will see if we can do further image optimization just also for the standard cameras that we have. And of course, for future to exploit the results that we obtain from RETINA and maybe bring the new technologies to the field. Again, here I have an overview of the different technologies that we will integrate. As these are still under development, we cannot show any results yet. However, our goal is to integrate the LiDAR sensor and the different multispectral sensors into one device that can be used in a medical environment. So even that's my part of the presentation, and I don't know if there are any questions.
Yeah, that's looks like it's a big part. Rochelle, thank you for the summary. So you got a quick question already in the chat about the wavelengths you used in the near infrared. I think that responds to those examples in the beginning on the surgery side.
Yeah, for the standard ICG, we have the approximately 780 nanometer excitation, and then we image the emission wavelengths from the fluorophore. And the other wavelength is more similar to parameters for the fluorescence of methylene blue. So it's around 680 excitation, and then imaging the emission a little bit higher wavelength.
Okay. And then the question that I already announced a few times, but this time for you. So is there something that you might benefit from when addressing the community that we have here of photonic technology experts in the room, or
so I think if there are any medical user needs that you are aware of, it will of course help us to also explore the broader application of this type of cameras. On top of that, for what we know for medical fields is if you can make something faster, more real time, that will always help, as we often suffer from motion artifacts in the medical applications. So that would be a little bit my question, so to say.
Okay. Well, hopefully there is some follow-up coming then after this meeting. So with this, thanks again for the talk, and I pass the word to our last speaker of the session, and also another exciting use case for our project. So this is Ana Rodriguez, who is the DAOHub Collab Beans and Wines Coordinator at Advit in Portugal. Hello, Ana.
Thank you, Ivan. Good afternoon, everyone. I'm just sharing the presentation.
There.
Okay. So I'm just going to talk a little bit about our use case. We are coming from the viticulture point of view of all this wonderful technology that we are talking today. So our organization is a collaborative laboratory in Portugal that has the principal aim to simplify the transition of technology between the universities and all the research groups and the wine business companies. ADVID, that is an association of different companies from this area, began at 1982, and in 2018-19 there was this recognition by the Portuguese government as a special interface organization, so we could help the companies working better with a science space. So we are 13 people working at this place, more than a half with a PhD in different areas of the wine business. We have 200 associates, mainly wine growing and wine producing companies, and also other industries that are related to this area, and R&D companies too. We have more than 30 projects ongoing, and 7 of them are international, also in different areas of knowledge. And we have 70 partners. More of these partners are wine companies, and this is what we work for. We are located in 2 different wine regions. Portugal is not so big in area, but we have a very different climate and geographical characteristics to all the countries. So we have several different wine regions with different wine styles, and the headquarters of this association is in the Douro Valley, that is in the northeast of Portugal. And we also have this hub that is quite new since 2022 in the Down region, is a little bit more to the south in Viseu. That's where I'm working from. And we also have this national work doing all over Portugal. So what brings us here and to this project is this special characteristics of the vines. We are talking about agriculture. Wine business is quite important in the agriculture business in Europe. It's one of the most important sectors in this area. So we are talking about knowing how to manage the vineyards in a more effective way, especially because of 2 real problems that we have now, 2 big risks. One of them is grapevine trunk diseases. That is something that is promoted by microorganisms and insects and so on. I'm not going to talk so much about that, but the fact is they low production of the vineyards in a way that can cause a lot of problems in what matters to economical return from these vineyards. So we have a low productivity and probably at the end a plant debt. So how we are going to try to see this, it's a little bit difficult because we cannot be inside the plant, but we can have some information by observing it. Unfortunately, we can only detect this when it is already making some damages. So we could have some information before, when the problem is still at the beginning. We could probably try to avoid at least the dissemination of the disease, because we can, this is like us, if a plant gets this disease, it's very easy to contaminate other plants, especially the usage of the material that we have and the equipment that we have to use at the vineyards. So as we don't have any curative treatments for these kind of diseases, it's quite important to detect them as soon as possible so we can take actions. And by this technology that we are speaking, LiDAR and multispectral or hyperspectral technology, we are trying to see if it is possible to prevent and anticipate this kind of contaminations. So this is one part of the issue. That is something that is spreading all over Europe. And another question is climate change. So we are talking about agriculture. It's something that is quite sensitive to climate change, and we need to be able to adapt to this climate change. So one of the biggest issues is the question related to water management, because we know that the vine is a plant that can survive in stress, but it has its own limits. It also has to do with the productivity of the vineyards. So what we are trying to do here is to see if we can have information that can be helpful to anticipate also some information related to water stress. So this is quite important, because knowing this, we can plan vineyard irrigation if it's needed, and to control it in what we want, considering what we want to the wines that we are going to produce with these grapes. So the question is that nowadays we can do this. Fortunately, it's quite a very heavy work, because we have to do it normally before the sun rises with this equipment that you can see on your right. What happens is that you have to get up really early in the dawn to do this, and we cannot have an information that is quite considerable in what matters to units analyzed, because we are going to analyze one leaf per plant to see what is the water condition of this plant. So we don't have any other way to do this in a more effective way. So we have a lot of human effort concerning this kind of measurements that we do now. We do it. We did this year, and we do it in another kind of projects, but it's quite a very heavy work. So using also these technologies that we were talking about all this afternoon, we are trying to anticipate this information through image that is much more easy. We already tested the prototype with Iman and Aeromedia this last harvest, both in Douro Valley and in the Down region. So we were trying to capture some images from the vineyards and also make these measurements and these observations in the vineyards to correlate the information that we can measure nowadays with the images that we were taking from the vineyards. So it was the first year, so it was all an experimental year. But this is what we were doing, so both at the Douro Valley and in the Down region. And now we are going to continue this work. So it's quite an end user experience, but we are quite hopeful in this technology, so it can help us to anticipate these kind of issues that are really disturbing in the wine sector economics. So I don't know if you have any questions. We are more focused in wine producing. So thanks for your attention. And I hope I could be quite well with the time. So Ivan.
No, it's perfectly done. Thank you, Anna. And of course, it's a very exciting use case for all of us to work on. I'd like to ask, what is the current actually mitigation measures to take that are taken against the GTD? Well, but also water content in wine grapes.
Well, in the grape trunk diseases, we are trying to educate somehow the viticultures to be very careful with the kind of material they use, the vegetal material, because probably some of these grape trunk diseases come already from the place where the vines are grown before they are planted in the vineyards, from the nurseries. And sometimes also when you are going to make some interventions in the vineyard, when you cut, for example, when you prune the vines, the material that you are using can get contaminated. So when you use it on other vine, you are propagating the disease. So the way we have to do it nowadays is, especially this, probably there are some other kind of interventions, but this is not very easy to control, even with the products from the industry. It's quite difficult, and that is why it's such a big loss in this area. And concerning the water management, well, it's measuring and decide what to do with the results you have. So I can tell you that nowadays in the wine sector, I think that most of the companies, I don't know if everyone, but the bigger ones are already having a lot of information from the vineyards to decide what to do, if to irrigate or not to irrigate. But then when you talk about climate change, the biggest problem is that even if you need to irrigate, you need to have water first. So what we can see nowadays, unfortunately in Spain, we are seeing the opposite in the south, but the truth is that most of the Iberian Peninsula was with a big problem with dryness during the last years. So this is the biggest question that we have to work on. It's measuring and deciding.
Okay. No, that's very well explained. There's a question from Mercedes at Tino. She wants to know what the LiDAR part adds to the infection detection.
Yeah, and if you want, I can answer this. Yes, for the ground platform, what we try to do with the LiDAR is to assess the orientation of the leaves, because one problem that we have working in outdoors with a hyperspectral camera is we are trying to not use active illumination. So there's a lot of non-uniformities or parameters that we don't have control regarding the light source because it's the sun. And what we have seen is that the orientation of the leaf can affect the reflectivity that we obtain, the spectral signature. So we are helping that it will, the LiDAR information will help to make more robust spectral signals for us, for our machine learning algorithms and for our the algorithms that work with the spectral information. This is for the infection detection, for the disease detection, and also for the water stress. For the yield estimation is because that it will allow us to calculate better the shape and the size of the grapes, so we will have better information about the size or the amount of grapes that we have. And I think we have another question, Ivan, before this one, that if the hyperspectral camera is worth the cost, and is a difficult question. They make sensors, and the cameras will, Carolina can correct me, but I think will be significantly cheaper than the current state-of-the-art hyperspectral sensors. For the current state-of-the-art hyperspectral sensors, it's only cost-effective if you have big vineyards that you can use the drone, I think. It's not my specialty to the commercial part of these services, but this is what I think. I think that with the new sensors that are way cheaper, it makes sense to have them. Of course, we have to see how much information we can extract from the state of the plant with these sensors.
Yeah, here maybe I will add, or maybe Anna would add it, but as she's mentioning that there are big losses incurred when you don't detect those illnesses of the plants in time. That's of course more expensive than any hyperspectral camera, plus all the human work. Typically, those hours of people collecting indeed leaves at that time, that's also a lot more expensive generally than equipment. And then, as Julio mentioned, then indeed also especially the multispectral snapshot cameras, they are already cheaper than the ones in the market. And the reason for indeed for studying also the going to quantum dot-based sensors is because that potentially also reduces further the price. So they are becoming cheaper and cheaper indeed. And in comparison to all the losses that you can have and all the time human effort involved in by not doing anything, that's I would say that that's always paying off.
Correct. So this was a very good question. So it indicates that many of our efforts are actually aimed for this, for making this also a cost-effective solution.
Exactly.
But yeah, okay. So thank you very much, Julio, Carolina, for taking the question, and Anna for a great summary of this use case. It's very exciting, and we're looking forward, of course, to hear the updates from you. So let me just share quick information with you, and I'll be closing this workshop. So this was the first workshop of a series of online workshops that will be provided to you by RETINA Project. We discussed the smart photonic sensor systems. And I'd like to thank again all the speakers that we heard from today. So Julio, Carolina, Peter, Francisco, Rick, Rochelle, and Anna. This was a great workshop. So altogether, I think we gave our audience a very good feeling of what RETINA aims to do. And also I'm looking forward to get the feedbacks from our audience and our speakers. So don't hesitate to reach out to any of the RETINA projects or to me and Julio as a coordinator of the project. If you have anything you have in mind, especially along the lines with what our speakers mentioned, what they might need from our photonics community in Europe. So with this, I'd also like to tell you that you can also get to know RETINA better if you visit Compamed Expo in Düsseldorf in next week. So we'll have a booth organized there for RETINA, and you have a chance to exchange with us offline. And similarly, at the end of January, RETINA is going to exhibit at the Photonics West exhibition in San Francisco, and our booth number is 500 to 5,200. So please don't hesitate to pass by, say hi, and share your ideas of how to make our project possible. With this, I'd like to thank all our speakers again, and also all the members of RETINA Consortium, and also for all of you for your attention today. Thank you very much. And
bye.
All right. Thank you very much. Bye, everybody.
Goodbye, Peter.
Thank you.
Goodbye, Francisco.
You. Bye.
Thanks.
Bye.
Thanks to everyone who stayed until the end. I hope you really enjoyed the talks today. So the room stays also open for a minute or two. So if you have something to exchange, please. Now it's an open microphone. And yeah, personally, I'm very happy with how it went. So I think now we have a little bit of public relationships opened. So we'll also take care of disseminating this later. So I think we will get for sure some feedback from the audience. This is the way to become famous for us.